Yeah, so I'm here. I'm sorry I'm not there. I would really like to be with you in the UK. I'm here in Brazil in the middle of the night. I'm Fabio. I work at the University of São Paulo in Brazil. I've been around SIPTA for many years. As you can see, I don't look like the photo that Alessandro found, but I'm here to start. So please, Alessandro, go ahead.
So, okay, should I say just something about the schedule of the day? So, you know, we have basically 4 different slots, and the first one is supposed to be a kind of introduction with the 3 of us speaking. Of course, Fabio will be starting, and then we have 3 independent lectures. The first one by Fabio in the second part of the morning, then Cassio will be talking about graphical models, and then myself will be talking on causal models. So this is basically the program of the day. Okay, we have these goals. So, okay, Fabio's, and let's say the goal of the first lecture is to kind of provide you some. Today is the AI day, so we want to say something in a broad sense about AI. Okay, in the second part, the second lecture, Fabio will be focusing on this link between probabilistic imprecision in AI by using specific topics. Not sure, Fabio, you want to say something now or just starting later?
Yeah, maybe I'll say it later.
Okay.
Go ahead.
Then Cassio will be focusing on probabilistic graphical models and how imprecise probabilities have been applied to and used with imprecise probabilistic models in the field of machine learning with different applications. And then in the last slot of the day, I will be focusing on the relation between causal analysis and imprecise probability. So this is the program. I think I leave the stage to Fabio. I stop my share, and I think Fabio, you can now start.
All right.
Great.
Can you hear me?
Yes, and we can see your screen.
All right. Okay, so I'll try to give a gentle introduction to connections between imprecise probabilities and AI, artificial intelligence. As Alessandro said, this is the Artificial Intelligence Day. Artificial intelligence is now a very hot subject. Lots of people talk about it. But actually, artificial intelligence has been around IDSIA and the society for a long time. There's been a number of people from artificial intelligence working in SIPTA like issues for since the beginning of the conference and the society. So this is something that has been around. I mean, this connection has been around. So I'll try to provide what I hope will be a sort of a gentle introduction for this first half an hour or so on these connections. And maybe I'll say some things about AI that are very obvious to everyone. Now you can turn on the television, you see people talking about AI all the time. So maybe some things will be simple, maybe some will be obvious, but I hope I'll go back in time and start presenting these connections as they happen throughout the years in a way that will be interesting to everyone. Okay, so let me see. So AI is now facing a very hot summer. It was a very hot topic, a very hot area, I would say. Every graphic, every picture that you see is like an exponential, presenting how many millions, billions, trillions of dollars are invested, how many victories are obtained in all sorts of areas. And it's a very pragmatic hot summer. Like, people are applying to many different areas, from health to financial services, and there's sharp interest from society. It's not just research or like business types. You have government and society thinking and discussing how to regulate it, how to deal with artificial intelligence in many ways. So AI has had some good times and bad times in the past. Is, often these bad times are called winters, the AI winters, as people say. We're now living through, going through a very hot summer, like I said. But still, there's a lot of debate. You can follow the literature and you see people discussing, what is AI? Is it possible at all? So there's still this discussion about AI, which seems it's sort of a never-ending discussion, because it's really hard to define what AI is. And there's a lot of concern whether it's risky or not, what are the benefits, the risks. Let me say a few things, just very broadly, I mean, general things. So I would take that AI is like the area that looks for devices that think or act in ways that seem to be intelligent. It's really hard to define intelligence. But I think there are two ways that people have addressed the issue. Of course, there are many ways, but I think there are at least two different classes of approaches. Some people are trying to do things that are similar to the way we humans do things. So people are trying to make the computer look intelligent, as intelligent as we are. Perhaps we're not always rational, right, as humans, but maybe you are interested in producing a computer that can interact with customers, and then it's not really necessary that the computer will look super rational, but it will be necessary that the computer looks like it's a nice individual on the other end. And then there's another class of approaches, which is like looking at ways to make the computer act and think rationally, following standards of rationality. And I think most of the people that are interested in imprecise probabilities from AI are really trying to look at things from the rational standpoints and from this approach. And then there are a few distinctions on the way people do things in AI. Some researchers try to get to a general AI, right? They will try to do things that at the end, at some point, the computer will pass a Turing test, or the computer will be super intelligent. And others are really more pragmatic. I think the more pragmatic types are really winning the game. They are really producing things that work and are useful to society. But then the AI they produce is not really human-like. It's not, the computers are not thinking like we do. They're doing things based on massive data sets, based on massive collections of texts, things that we do not do. Most of what the best models today do is they collect lots of data, and they will extract patterns, and they will present the patterns in an intelligent way. They will look intelligent, but they will not think the way we do. And then there's another distinction that I would like to make, which I think is interesting for the purposes of explaining broadly what AI is doing now, which is some people are neats. This is an expression that was used in the 70s. There are neats and scruffies. So the neats are people who are looking for mathematical analysis and a mathematical basis for intelligence. And the scruffies are people like just, well, let's build things and see and then try to make it work. And I think the scruffies are really winning the game now. People are building big systems that are really working. If you go to a textbook, in AI textbook, you see things like this. You see search, it's the computer science stuff. You see people discussing planning and decision-making, knowledge representation, and machine learning. And then there's a bunch of other topics like vision, robotics, that may appear in a textbook, in an AI textbook. But I think we can prune this to a shorter list of things. I mean, what are the basic boxes that AI should take care of? And I think there are three really key ingredients that people are trying to put together. There's knowledge representation reasoning, like you have to represent knowledge, you have to reason about things. And knowledge in AI is a very vague word. It's not just beliefs that are true. It's just that there's probabilities, representing uncertainty. All of this gets into knowledge representation reasoning. And then there's decision making. So an intelligent actor has to decide. And then there's planning. So it's just one decision maker, one artificial intelligence deciding sequences of actions. And then there's negotiation. There's lots of agents negotiating and then maybe making decisions together. And then there's a third box, which is like machine learning, which is you have to be able to learn somehow. You have to be able to learn with your experience if you're intelligent at all. And then there's like statistical learning. There's like old discussion, old category of statistical machine learning. And then there's neural machine learning, which is like people trying to build neural networks. And today, if you look at the literature, you see things are like this. There's a little bit of knowledge representation. And actually, there's a lot, but the area has grown so much that if you look from the distance, you see a tiny spot. Some people doing knowledge representation reasoning, some people doing decision making, lots and lots of people doing machine learning. So that's what's happening now. And I think the reason is that machine learning is really working because we have so much data. Now we have so much computing power that we can actually process the data that we have. And there are some insights. You know, the last 20 years have brought some insights on how to process the data and how to make it look intelligent. Let me go back in history just from this perspective of what AI is now, and let me go back a little bit and see how AI has evolved and how it's being connected with uncertainty, and in particular with imprecise probabilities. So if you go back, I mean, AI is 70 years old almost now. It started around 56. People at the beginning were trying to solve problems by searching for solutions. So there was a question: how do you represent the problem, and how do you search for a solution? So that was the effort. There were many efforts. One of the famous ones was the general problem solver by Simon and Newell. Here they are, as two important figures in AI. So they were concerned about representing a problem and then searching for a solution. Okay. At that time, AI was not close to probability at all. In fact, some people were against using probability. If you go back and read a famous paper by McCarthy and Hayes from '69, it's a long time ago. The paper is called "Some Epistemological Problems from the Standpoint of Artificial Intelligence." There is a point where they discuss uncertainty. They discuss whether it's appropriate to deal with uncertainty, and they write that any formalism that requires numerical probabilities would be epistemologically inadequate. So, and this was something that was accepted for maybe 25 years. The argument was that probabilities were not available. It was not easy to get them, not easy to handle them. And here you see McCarthy working back then. And then what happened was there was an AI winter in the 70s. People sort of were less interested in AI. And then when he came back in the 80s, he came back with an interest in expert systems. Now, expert systems are systems that try to encode, to reproduce the behavior of experts. And what the systems of the time, what they did was they collected rules, rules such as this one in blue. This rule says if the site culture is blood and grand organism is neg, morpho-organism is rod, and birth patient is serious, then you reach some conclusion. So all these expert systems of the time of the 80s, what they did was they collected rules, they offered facilities so that you could manipulate these rules. And then there were famous systems back then, Prospector, Caduceus. There was a very, very famous system from Stanford University called Mycene. Mycene was was a system that tried to reproduce the medical behavior in several areas. And it came with uncertainty manipulation, handling. It handled uncertainty in some way. What it did was, if you look at the rule here in blue, there are several ifs, if this and this and this and this, and then there's then identity organisms pseudomonas, but before the identity, you see a number. So this number was supposed to carry the uncertainty of the rule. So if these things happen, then with confidence 0.4, the identity of the organism is pseudomonas. And the reason I said confidence is, this was not supposed to be a probability. This was called a confidence factor. It had special rules. We did not follow the rules of probability. And then around 86, 87, 88, there was an explosion of interest in AI, in dealing with uncertainty in AI. So people try to develop logical formalisms, try to get rules, logic basic rules and formalisms that capture uncertainty. And then there were confidence factors, these things that appear in my scene. Confidence factors were interpreted as Dempster-Shafer theory objects, in particular belief functions. So perhaps this is something that will be touched lightly by Alessandro later, the idea that you can handle belief functions. Then some people were very interested in possibility theory back then. Some people were interested in probabilistic logic, and I will, in the second lecture, talk about probabilistic logic, because probabilistic logic is really the way imprecise probabilities got into the artificial intelligence mindset at the time and since then. And even probability intervals and all sorts of things that we now look into within IDSIA. And then even probabilities. And then even people try to go back and say, look, let's use probabilities. This thing has been around for centuries. So, and what happened is the formalism of Bayesian networks was invented by Udea Pearl. In fact, in '86, he published the first papers, and then he published a book in '88. The book was reissued in '91, and then it took off. And Bayesian networks became really popular in AI. And this is something that we will use throughout our lectures, this formalism. And Cassio will provide a summary of the theory of Bayesian networks in the second part of this first lecture. So I will just skip and I will just say, look, this is a formalism that will allow you to represent probabilities using graphs in a visually interesting way. This is one Bayesian network, but Cassio will describe others and discuss and define concepts. So people were looking at representing uncertainty back then in the 80s. At the same time, people were looking at planning. They were looking at sequential decision making. They were looking at, well, how do I start with a table filled with bananas, and how do I eat a banana if I'm a robot? That was the sort of thing that people worried about. And there were languages to represent actions, to represent results and consequences of actions. This is one particular language that was really popular, still is popular in applied work. So in this language, you write down the initial state. You say that there are bananas at B and so on. You say where you want to get. You want to get bananas, you want to have bananas, and then you list the actions that you can take. So you say, well, look, if there's something at the table and it's low, and if I can take it, then I'll take this action, I'll take it. So this is the sort of thing that you had with back then in the 70s and 80s. And then people started to realize, well, look, we need to deal with uncertainty in decision making. If we're making sequential decisions, we have to take care of the uncertainty that will inevitably appear. And then people start to look at tools from operations research and economics management. The tool that was really most popular and still is popular, very popular, is the Markov decision process formalism. Okay, so in this formalism you have states, Like here, you have standing, moving, and falling, and you can move around. You can take an action. The action will produce a result. It will move you to another state with some probability, and that's where the uncertainty comes. And you get rewards or you pay costs. So you have states, actions. You have transitions between states, and the transitions are probabilistic. And so what happened in around the 90s was that people started to realize, well, look, if we now have this formalism of Bayesian networks, and now we can handle uncertainty through probabilities, maybe we can actually apply this to planning problems under uncertainty. And even then, even at the beginning, and even in the literature that people used, like even in the 70s, people using Markov decision process were concerned about where do you get the probabilities and how do you represent probabilities that are not precise. So the theory of Markov decision processes has been always followed by interest in Markov decision process with imprecise probabilities. And this name came actually before SIPTA. People used Markov decision process with imprecise probabilities even in the 70s. And so we will discuss these objects later in the second lecture. I'll spend some time discussing them, Markov decision process and Markov decision processes with imprecise probabilities. I think this is really something that where the connection is important. But what happens now is that we have really a world with lots of data, lots of big data, and we have computers that can extract patterns and follow these patterns and turn the patterns into really interesting applications, okay? And so there's enormous interest and enormous, lots of results coming out of this data-driven machine learning. An area where probabilities are fundamental because you're basically dealing with statistics. And there's one paper that I would like to mention that I think is really interesting reading. Is this one by Halewi, Norvig, and Pereira. These are people from Google. And back in 2009, so this is not news, more than 10 years ago, they wrote this paper on the unreasonable effectiveness of data. And their argument is this, basically, that it's amazing, it's unreasonable how intelligent you can look if you just extract patterns and try to follow them. It's really surprising that you can look this intelligent, but you can. And today, that's what most people do in AI. You just follow patterns, extract big patterns from big data, and follow them. I guess I will just, in the interest of time, I'll just go quickly through a few comments here. This is one example where this data-driven machine learning approach has shown really dramatically. There's one problem in language processing. It's called the Winograd scheme challenge, which is this. So you have a sentence. In this case, the trophy would not fit in the suitcase because it was too, and then you choose, okay? Because it's too small. So if you have this sentence with small, and then you ask, what is it? What is it that is small? Immediately we know that it's the suitcase, right? Because the trophy goes in the suitcase, and then the suitcase must be small. And if I say the trophy will not fit in the suitcase because it was too large, immediately you know, well, the trophy is large. This is too large. But there's a lot of information that we have about the way the world is that we're bringing into this understanding of the sentence. What exactly is small or large, depending on how you choose the sentence. So this was the problem that Terry Winograd and this guy here proposed in the 70s, really. And it was a problem that computers were the performance of computers was really poor in deciding which object was the referent of the pronoun, it, right? But now it's simple for computers to decide this. Why? because, well, we have so much data on language, we have so much text, we have so many documents to work with, that people can extract all patterns of usage for pronouns, and they will, computers will just choose correctly the object, okay? So this is the kind of thing that has happened. One thing that happened is that people started using all sorts of statistical methods. So I listed here what you can find in artificial intelligence book today. Some artificial intelligence books now are just statistics, and just have all sorts of statistical methods. And one winning kind of technique is the neural network. Okay, this has people excited all over the place, even like in movies, people are talking about neural networks. So there's the traditional neural network, which is basically you have inputs. Here you have x3, x2, and x1. And then a neural network is really a simple thing. It's you get the inputs, you multiply them by weights, and you get them through a some very simple nonlinear function. In this case, I'm using the so-called ReLU functions. These are simple functions, don't worry about them. And then you get the outputs and you multiply by weights and you pass through nonlinear functions, and then there you go. So this is a neural network. So these things are nonlinear. They are supposedly difficult to make them work, but you know, they are working fine. And in fact, today you can use very large neural networks that have many. So you can see in the picture here that you have layers, right? You have the inputs at the left, and then you have layers of these functions. If you have many layers, you have what's called a deep neural network, and you have deep learning. And deep learning has been very successful, so people can now interpret images, text. So this has become the really hot stuff in the field. There's an ongoing debate, and this is a topic that I would like this is something I would like to mention. There's a debate within machine learning whether we should differentiate between epistemic and aleatoric uncertainty in machine learning. Some people have written about this, and maybe I think our community is perhaps more used to these terms and in different contexts, and perhaps we have better terminology for these things, but people are trying to understand. And usually what they say, what you see in the literature is that aleatoric refers to random disturbances, and this is something that supposedly the neural network will capture. And epistemic uncertainty refers to the lack of modeling, understanding, knowledge about the domain. Maybe this is something that the neural network cannot possibly capture. And there have been papers trying to model the epistemic side here using Credo sets and tools from Imprecise probability. Okay. In fact, there's been a recent paper with several authors. One of them is Sebastian de Sterk, one distinguished person from the IP community, on how to use Credo sets to represent epistemic as opposed to aleatoric uncertainty within machine learning. And then there's this thing, I will just mention this quickly because I want to link to something that Alessandro will address later. There's all this discussion about risks of AI. Some people will go for this utopian idea that there will be increases in productivity, better services. And then there's people sort of negative and thinking that computers will be out there killing people and stuff like that. So I will not get into this debate too much. But I just want to mention this, that there's real concern within the artificial intelligence community that if computers get intelligent, so to speak, without a controlling environment, then you may have problems like people will lose control and will not understand it, will not understand what the computer is doing. People will sort of have less trust in what the computers are deciding because they don't understand what's going on. So I will say some words about this particular fear here. That is the fear that as artificial intelligence gets more powerful, there will be a loss of control, maybe a loss of privacy, a loss of understanding of what's going on. Okay, and I'll leave these other fears to other people to discuss. And I guess these are important things, but they are not really things we are interested in right now. And then there are errors, and not just it's not just simple errors that you have now when you apply machine learning. So let me give you an example. This is a famous example in a paper by people from the Harvard School of Medicine. So here's at the left, you have an image of skin image. It has something in it, and a neural network was produced to decide whether this image carries a tumor or not. There's a benign or malignant tumor. And this neural network says that the leftmost image is benign. Okay, you can see it's almost all green. But then what they did was they disturbed the image a little bit, just a little bit. So they added a little bit of noise to the image. And you get the image at the right, which to me seems like the same image. Okay, there's no difference that I can tell. But this image at the right, through the neural network, will appear as a malignant tumor with almost complete certainty. You can see here. Now, why is that? So people don't understand. Why is it that the neural network change its mind in a way, right? So understanding the errors is a real challenge today, because we don't really have an understanding of what's going on inside these black boxes. And then there's interest due to these reasons, due to an interest in understanding what is inside this black box. There's a lot of interest in interpreting and explaining machine learning. And there's a whole endeavor now that is referred to as explainable AI that looks for techniques that can explain the behavior of these complex models. So basically, the setting is this. So you have raw data, you have all these complicated machine learning things, and then you have sort of a user who cannot understand what's going on. If there are errors, he will not know why. And maybe there are no errors, he doesn't understand why decisions are made and why decisions are the way they are. So how to explain these decisions to the user? This is the goal of explainable AI, which is a really hot topic now. It's been a hot topic since.
Sorry, I don't mean to interrupt. We have a question from the crowd about just one previous slide. Is it okay if we take that?
Yeah.
So Matthias asks, question, this is about the adversarial, Matthias.
Okay.
Ask whether this is just a result of overfitting.
Well, I guess it must be, right? In the sense that the neural network is so large that it captures all sorts of patterns, and then it's capturing even this noise in a sense. So it's really overfitting. But the problem is that saying that it's overfitting does not help, right? So okay, it's overfitting. So why is it happening? How can you fix it? These are the difficult things when you have these really large black box models. Is that clear?
Yes, Matthias thinks so.
All right. Actually, can you hear me? Is that okay in your end?
Yeah.
All right, so let me go ahead. So this concern about explainable AI has been around for 5 years now. About 5 years since DARPA, the United States Army branch of research, they put together, they announced a large funding effort in explainable AI. And this is a picture that I got from their documents, their 2017 documents, where they say, well, look, this is how machine learning is today, and this is how it has to be. You have to be an explainable model between these black boxes and the user. Okay. All right. So this is what I wanted to say at this very initial half hour. So AI is going through a very hot summer. It's very hot. I guess I don't have to say this. Everybody knows. But the AI that is working now is very pragmatic. It's really scruffy. Like people trying all sorts of things. It's not really the ideal AI that is really rational and you know the principles. And so no, it's not even trying to pass a Turing test. It's just trying to solve problems that are practical and useful. It is really data-driven in the sense that the main thing is to get data and extract patterns and reproduce them. There is now, and I think this is one of the main things in AI now, there is now a hot debate on how to mix data-driven AI, which is the thing that is really working, and knowledge-based AI, which is where you represent rules, uncertainty, you handle them from principles, you try to make decisions that are sort of rational in a way. And then there is interesting what's called neurosymbolic AI. Neurosymbolic AI is I guess a name for this mix. You put together these data-driven things and knowledge-based symbolic techniques. There's interesting knowledge-enhanced machine learning. So you get machine learning and you enhance it with representations that can handle symbols and more formal reasoning. And I guess from the perspective of this school, right, I should say this. I hope I made enough links that I can say this now, that throughout its history, I mean, throughout its 70 years, AI has been very interesting formalists that deal with uncertainty. Not always, it's not at the beginning, not with probabilities, but since the last 30 years at least, since the 90s, AI has been very interested in, I would say since the 80s, maybe around 40 years now. AI has been very interesting formalists that handle probabilistic indeterminacy and precision. This has been really something strong in AI. And things like probabilistic logic and probabilistic argumentation, they have been around for a long time. I will discuss them in the second lecture. Credo networks have been around as a counterpart of Bayesian networks, and Cassio will discuss this in the third lecture. There is now very interesting work in causal reasoning. This is being a very hot topic in AI, and there's a clear connection with imprecision in probabilities. This is something that Alessandro will discuss in the fourth lecture, the last one. And there's a clear connection between imprecise probabilities and sequential decision-making in AI through imprecise Markov decision processes. This is something I will discuss in the second lecture. So I hope we will, through the day, get these connections in more detail, and maybe they will become they'll become clear to you, right? So that's our purpose here. I guess I'll conclude and finish and stop here. Thanks a lot. Thanks a lot.
So I will take over, but it will be interesting to know if everybody can hear me and see the slides online. Fabio, can you help with that?
Yes, I can see it. I can hear you.
Okay, that's great. So the second part of this first part, it has a different flavor. Well, but first of all, let me do something that before I forget, and it's very important, is to thank the organizers for this really great event and this very large crowd here, and this is very nice to see. So let me thank them and thank for the invitation to come to speak. So back to the topic. The flavor of this part is completely different from what Fabio just did. So I will just dig into one topic, and the reason for this topic is that we will be using it later multiple times. So you're going to see that the slides and the content here from very broad gets us into something very narrow very quickly, but because we need later on. So please bear with me, this part is to build on what we are going to do later, and there is no actually imprecise probability in this very first part. So we have here as an example initial setup, and many things here will be simplified just for us to discuss them together. It doesn't mean that the models or frameworks are limited to this kind of example, but the first thing that I'm going to do here is to work with binary variables only. So we can say that those have just two possible states, as true and false. And I will start with this example, which has 4 of those variables. The first one is high temperature, could be true or false, the fitness of a goalkeeper and the fitness of attacker, and whether we win or lose a match, so win being true or false. And a possible way of representing knowledge over this domain, imagine that those are variables we are interested in, and let's say we don't care about anything else. So we care about those 4 variables, is to define a function, a mass function for these 4 variables. And this could be used to represent our knowledge that we have about them. And, and we can build this function from data, from constraints, from experts. And in this formalism that I'm going to talk here, discovering or finding this function it's called learning in the context of these graphical models. And we can use this function, which we have to somehow encode in the computer into bits, and we do this in different ways, to compute queries or to try to extract some information from that function. And this could be, for instance, to compute what is the probability of high temperature, given that we win the match. Or it could be something more on the decision side, which is what's the most probable value for the x sub 4, so win the match, given that there's no high temperature, so high temperature is false. That's another possible way of trying to extract. And if you have this function, this P, this joint P, this is usually called reasoning or inferences in the context of this graphical model. So you're just trying to take from this function and compute something. So something that is not directly given to you, but it's there inside the function. So you just have to manipulate the function and get the number out. So with this function, we have a few, I'm creating here some terminology, a few different ways of computing with it. The first one we call the belief updating, and that is when you have to compute the probability of some event, giving some observations. So just the previous example, in this case, what's the P of x sub 1 equal to true, given x sub 4 equal to true. And this kind of computation is used when you're trying to learn the model for classification and many more. You could compute something that is for the decision. So what's the most probable value? Also in the example before was what is the most likely are you going to win or lose the match? So this is to compute the most probable configuration of some variables given evidence on some others. And this has 2 flavors. Either it's all the variables are involved in your query, so you want to know the value of all the variables, giving all the others as evidence or observed. So meaning here, x1, x2, x3, and x4 all appear in my query. Some of them I want to know the value, some others are given as evidence. And this is often used for multi-label classification if you don't have missing data. Or the partial version of that, which was the example before. If you look in that example, x2 and x3 does not appear in the query, so you have to sum over those if you have that big table, right? Because x2 and x3 are marginalized. So in this case, the probability of x4 given x1, and you want to know what's the most probable state for x4. And this is, for instance, used for classification with missing data. Why I mention all those type of queries? Well, this is type of things that you easily compute, and often in probability statistics, you don't even call these as reasoning or inferences or anything, because if you have the table, it's something trivial. So isn't that like so trivial, this task? It is actually very trivial. If you have the table, it's there, you just really go through the table, collect the information, sum up some rows, take the maximum value of some others, and that's it. There's not much more to do if you do have the table. So let's talk about these probabilistic graphical models when you do not have the table. Why wouldn't you have this big table? Imagine now the number of variables grows. So in that example, I had just 4 variables. They are binary, so all possible configurations you can think is 2 to the power of 4. And this is just 16, and you can have that table and you can store easily in a computer. But let's say now that you don't have 4 variables, but you have 30 variables. It's not that much. But 2 to the power of 30, it starts already to be hard to store in a computer. You can still do it, but go a bit further. You cannot even store this anymore, right? So we need something smarter to work with these high dimensional problems. And nowadays, as Fabio was saying, having 30, 40 variables actually is on the low side, right? For many problems in machine learning. So how we deal with that? Well, we still want to have a global model. We still want to have this function that is a function that specifies all my knowledge for all the variables I have. And this example now here have 8. So from 2 to 4, now we have 2 to the power of 8. So we would have, this table would have 256 states. And let's imagine that your computer is very small and 256 is already too large for you to store in your computer, right? In one way, this might be a joke. On the other way, it may be you have an embedded system in a very small, I don't know, tiny chip and processors inside an agent around. So that could already be the case, that 256 is too big. How do we deal with that? One way is, well, let's decompose that function in smaller functions, induced by a concept of independence, and let's make use of that. So instead of having just the whole table, let's try to find some relation, independences or relations among those variables such that we can use smaller local functions. When we multiply them, they induce to us this big global function. So in the example here, we could have 4 local models, each one over 3 variables only. And when you multiply them, you get to a larger function that specifies the value for all the 8. So if you want to compute with those 8 now, you don't need to deal with the table that has 2 to the power of 8 elements, but to 4 functions, each one with 2 to the power of 8 2 to the power of 3 elements, so 8 each. We have a.
What do you mean by multiply? There's a normal multiplication.
Yes, it's a normal multiplication, but I will get more to that in a moment. So the idea is that we want to decompose this large function by making use of some knowledge that we have or learning that from data. And in the case of Bayesian networks, we can represent this with a nice graph. And the graph has a condition behind, so an interpretation of this graph that is very useful. So these graphs come in 2 flavors, or at least the most common ones. Actually, there are way more flavors, but let's say the 2 main flavors. I will start with the undirected one because it's easier to explain, but we are not going to talk about them later, just this slide. And the flavor is, let's say that you have all those variables and now you draw a graph that specifies the dependencies among those variables. And in the top graph here, what you have is that you can induce a condition or force a condition on the graph to specify the joint model based on smaller models related to the Markov condition of the graph. In the top one, we would say that variables are independent if they are disconnected or if I give something that disconnects them. So X and Y are independent given Z if any path from X to Y contains an element of Z. So if you think about that, the graph now is telling you a way of breaking a big function in smaller functions if I have a condition that can break those functions by independence. So if you give, in the example, X, Z sub 1 and Z sub 2, if you give the value of those two, X and Y are independent. But if that is the case, then I don't need a function that specifies something for all of them at the same time. I could break it into smaller functions. And this is really multiplication only, but it's not just multiplication, it's a valid multiplication because of this independency that is there behind. But let's forget about the undirected because we're not going to use. We're not going to use, right? Okay, we are not going to use. Fabio, we're not going to use, right? So we are going to use Bayesian networks a lot through the day. And for Bayesian networks, the condition is a little bit more complicated if you think about the paths. But it's easy to talk about parents and children in the graph. So first of all, a parent of a node are those nodes that have an arc leaving from that node to another. So the one that has the arc leaving is the parent, and the one that has the arc arriving is the child. Okay, parent, child. So now I can talk about descendants. Well, descendants are all those that have a path, directed path from that node downwards. Naturally descendant. You can also talk about ancestors, then you follow the direction against the arrows. And if you have these graph definitions, now we can create and define a nice condition, which is if I give you a graph and this condition that given the parents of a node, every node or that node is independent of the non-descendants. With that condition, you can break your large function into smaller functions in a very meaningful, interpretable way. So if you want to think about paths as before, then there is a concept of deseparation. And the concept is a bit harder, and I can come back to it in a moment. Or after I show some examples, then I can talk about that one. So with directed graphs, we are choosing them because they help in dealing with sampling. Distributions are normalized. The edges can be used for causal inference, and the representation power compared to the undirected is basically the same. So we are talking mostly about directed models. Though the Markov condition is a little bit trickier to explain. So this is how the model looks like. So you have a bunch of variables. They are connected to these nodes of the graph. It's the same example back. So you have x sub 1 to x sub 4. The Markov condition says that the node is condition independent of known descendants given parents. And if you have this condition, then what you're going to see is that somehow you are breaking the probabilities into the probabilities of each node given the parents. And then you can multiply them to obtain that joint function that you had before. So in this example, the function for x sub 1 to x sub 4 can be broken exactly on the node given the parents. So if you look to the terms on that multiplication, which is really just a multiplication, you have the p of x1 times the p of x2 given the parents of x2, so given x1, times the p of x3 given the parent of x3, which is x1, times the p of x4 given the parents of x4, which are x3 and x2 here in this. So that condition, because of that independence, basically you are taking chain rule of probability and dropping some things, exactly those that are your variable independent, which are exactly the non-parents and non-descendants. And then the chain rule basically simplifies to what you see here on the lower right side. And this will be the case for the Bayesian network always. So if you look to the lower left side, you have the definition of the Bayesian network as being a set of conditional mass functions for the node and the parents. So this is the P of x sub I given the parents of x sub I. And it defines one joint mass function by multiplying them. Multiplying exactly in the same way as the example on the right side. So x given parents of all of them. And this is induced by the condition that we just saw in the previous slide. If you want then to talk about independence on this graph, you have this separation, and you can say that x and y are separated by z if along every path of this that you find between x and y. Now you have to look to directions. So there must be a w such that the w has converging arrows and is not in the observation, or it has leaving arrows and is observed, which is the case here of x. So in the example here, z1 and z2 are independent given x, the parent, but they are not independent given y. So y connect them on the other way. So we come more to that when needed later on. What I have included on some slides for you here are some R code, which you can download if you want. And I'm going to, oh, sorry.
Sorry, just a small question. Do you allow loops in Python networks?
We cannot have the loops. And I have an example just mentioning that in a moment, but it's the same problem as you could not have a loop if you just think about probability and chain rule. So you're just breaking. So if you would have the loop, then basically is the same as talking about losing the normalization. And you could have a loop if you think about undirected models. But you would not have the directly correspondence to these local models being probabilities. They would be just like weights that you multiply, and then later on you would have to normalize. Okay, so to avoid and to keep normalization and everything interpretable, we cannot have the loops. So let's see if you can read this. So this is my surname, .nl, and SIPTA School 2022. If you want to download those files and play later, you don't need to, okay? It's not going to be needed through everything here I'm going to be doing and working, but just in case you want later on to get the files. And I will update them as soon as we find bugs on them, and we will likely find some bugs on that. So later on you can find the full version there. About the loops, maybe it's worth mentioning here. So what we are doing here, let's take 3 of them here very quickly. So you could think about just a way of factorizing a distribution, and there is no Bayesian network here. I'm just using a chain rule and factorizing this into pieces, right? If you combine those two and combine, you get to that, just probability. What the Bayesian network is telling you based on the parents and so is that some of those you may eventually drop because of the independence concept. And when you drop them, exactly because there is no arc among them. And so this means that the same chain rule is being applied, just there are some independencies there. So all the normalizations are still valid because it's just the chain rule plus some condition independencies that you have in the model. The loop would break that. So the example here is creating a Bayesian network with this package, BNLearn. So you have the CPTs being defined. I will go into more details on at the beginning of the afternoon. And this is just a taste of a little piece of code creating a Bayesian network. It's creating the local models one by one. First, and it's exactly our example of before with the goalkeeper and so. So X1 has no parents. Then X2 has X1 as parent. And you can take a look on the file later, but I will go in more details later on.
I'm not mistaken. In Bayesian networks, you most avoid loops, right? Because I think you can compute in loops, or you can actually.
If you have loops, then you would not be a Bayesian network.
Yeah.
And the local components of this product would not be probabilities anymore. And right now they are actually conditional probabilities, but they wouldn't be anymore. But you could compute with that. It would be, you could make that into a Markov network or Markov random field or an energy model, as now is more fancy to say. And then you could compute with that. But each one of the pieces would not be directly corresponds to a probability value there, a conditional mass function. Yep. And then we would not call them Bayesian networks. So we can run some queries with this code and really don't bother so much about the details. I create a few functions there to make this, to play around a bit later with you and the code. And in this example here, for instance, we query variable 2 with state false. And then when we call that inference, we get what is the probability of X2 being false. In this example is 84. And the way I'm doing these computations here is in the most inefficient possible way. And you're going to see that in the code, but it's just to get numbers, not to be efficient. And there are a few other examples also if you want to compute the most probable value of a variable or combinations with evidence. In this case, X1, X2 given X4. Or if you want to compute what's the most probable value for all the variables, you can also do that. It's called the map query. And you can also keep changing this, and they're just examples of using that small package. We will come back to this later. So if you want to know now how we do the computations, if you have a Bayesian network, well, you don't have that whole table anymore. You could generate the whole table, but you don't want to because it will be too big. So how we do then to compute if you have a Bayesian network? So you are going to try somehow to solve that equation without having to compute the whole table. That equation, the way it's written there right now, it's actually computing the whole table because you first do all the products. Every time you do the products, inside is basically one of the values of the table. And then you sum over those that you want to marginalize. So if you just apply the function as is there to compute the P of XQ given XZ, you are actually creating the whole table. But what you can do much smarter, and it's what we do with Bayesian networks, is because of the conditional independencies, you can switch some positions of sums and products in a smart way to avoid computing the whole table. Okay, that's the whole thing to make this efficient, and it's as efficient depending on how your graph is. And the same thing for the version that you do the most probable computation. In this case, you want the max of XQ. And again, you have to sum and multiply and take the max over some of the other variables. So doing this is NP hard, meaning we don't know any way to do this in polynomial time, roughly speaking, unless the graph is very simple. So the graph has some conditions such as it's a polytree or has a bounded tree width.
I'm curious about the hard. It's in relation to what number of nodes and the number of things.
Yes, so it's typically done this with respect to number of nodes. And you're right. So I wanted to make this connection. Why I mentioned this NP hard. So if you had somebody gives you the full table, then and you can start the full table, then this is efficient on the size of the full table because the full table is exponentially big. So you're linear on the full table size. But now with the Bayesian network, you don't have the full table. Somebody gives you a much simpler representation. So you need way fewer bits. And now it's hard on the number of bits this person is giving you to encode the Bayesian network. So more formally, it's not really the number of nodes. It's really the size of what you need to give you the Bayesian network to someone in a computer-friendly manner, or the most computer-friendly manner you could. There are a few different ways of factorizing, as you can imagine. The simplest, I would say, is that if you assume all the variables to be independent of all the other variables, so you just have the product of the margins. And that's a valid Bayesian network without any arcs. It's a possible structure for a Bayesian network. But you could also factorize in a way that you have a full graph. In this example, you're going to see that X4 has all the others as parents, then X3 has the other two, X2 has the other, and X1, wow, this is a chain rule. There is no independence at all. Nobody's independent of anybody. It's still a valid Bayesian network, but that's a very big one. Actually, this is as big as the full table. And you can get this in a different order. So you could have the chain rule applying from 1 to 4 or 4 to 1, and it's another Bayesian network. But it represents, well, has the power to represent the very same distribution because it's just the full table again. But Alessandro will tell you that, well, maybe you care about the direction of the arcs. Right now, I'm not that caring about the direction of the arcs. I'm only caring about the independences that are induced by the arcs. And you could have the example we were talking about, just in the other slides. In that case, the X1 has no parents, 2 and 3 have 1 as parent, and 4 has 2 and 3. Is the diamond that we just saw. That would be the factorization and the structure of the example we saw before. And you cannot have loops. So this one is just to say, well, that one is not valid because you're going to see there is a loop there, no loops. Key fact, and connects to the just question that we had about the NP hard, is that the size of this model is quite small. Because of this factorization, every one of these local models is small, and you multiply all of them, you would get the big table, but you never write down the big table. You just keep the small models in the computer, and you want to compute with that without having to go through the big table. Disclaimer, my code there creates the big table. So if you try to use it for large Bayesian networks, it's not going to work.
Is there any drawbacks by using that factorization?
So the question is if there are drawbacks on the factorization. Yes, if the factorization does not hold. But then we are going to discuss this. So like if we assume an independence that is not there, for instance, right? Because then we make a mistake. That's the drawback. But if you know the independence is there, then there is no drawback. You should use it. We are going to talk more about that, even to the point that we assume so many independences, and typically they're not true, and still the model is pretty good. But that's a different point. Sometimes we go for simplicity and allow us to make mistakes just to create a better classifier, maybe.
Just following this, so I think that the same function is just not assuming independent. Like,
yes.
You want this completely correct.
Yes.
You would be saying,
That's true, and that's a very nice point. So the question is, why not to use the full table? Because then you're safe, you're not assuming any independences there. True. It is a trade-off between the amount of computational power you have to store that, and also amount of data if you want to learn that. So if you want to learn this big table, you need way more data because you have way more configurations to learn, free parameters in the model, if you will. So it's a trade-off, and that's why sometimes you just assume some independences even if they're not there, because you have fewer parameters. You might have a model closer to the, let's say, generating model behind. I didn't even talk about that, what we want to do with those models, but that's really the point there. So computationally and even in terms of data, amount of data, it might be better to sometimes make mistakes. And we have to find a trade-off, yes.
Is it also possible that the full table is just literally not available? For example, in the example of games that maybe you just didn't play during like that weather or that certain combination that you don't remember?
Sure. So the question is, can you generate the whole table? Yeah, so the point is exactly connected to the amount of data you would have, right? If you have the full table, let's take the example with 2 to the power of h. 256 cases would be there. Maybe some of them you're never going to see, but you don't see them just because you don't have enough data. If you would have like more and more and more and more and more data, then everything would be fine. This would converge to the proper proportions eventually. And what you see there is what you get. The table is fine, everything is great. But if you don't have enough data, and we never have enough data. So think about 50 variables, binary, 2 to the power of 50. When are you going to have data even enough to have one case of each? You can't, if one of case of each is even possible. You won't only see a very small spot of the whole universe of possible cases that are there, unless you have enforced some independencies among them. Because then the amount of data you need is only proportional to the size of your local models, because you learn the local models. That's where the data hungry is, on the size of the local model, to learn those parameters.
Would there be a way to put a fire on the structure of the network or the architecture, so that as more data are collected? Yeah.
How do we learn the structure? So there are different types of structures and complexities, and that affects how fast you do computations. I'm not going too much in detail here, but just to tell you, these models are faster as they are similar to trees. So you have here what's called a tree, meaning every node has at most one parent, and then polytree, meaning that if you drop the direction of the arcs, then it becomes a tree. Then you have a naive structure, which is even simpler. Everybody connected to one single node and nothing else as the parent. And then you have a general case. And the general case, actually, there is this definition of tree width. But let's not go too much there. You can read on the slide later, but it's just tell how close how similar you are to a tree. If you want a simple definition is, if you could embed your thing on a hypertree, how large would it need to be the nodes of this hypertree to embed your graph into that? Okay, that's kind of like the similarity tree. And then the complexity of queries are related to this, to trees. And that is how we have different networks and the learning. So how we learn this? Two different ways. Either we create a score and then try to find a structure that has the best score based on data. And if you have more data, you may allow this to be more complicated. If you have fewer data, maybe simpler, right? But how you define this? Well, we could do a Bayesian approach and put a distribution on the possible graphs, and then do an updating on this, and then compute the one that has the highest posterior probability, given the data you saw. You could do a maximum likelihood, plain and simple. Obviously, if you do a maximum likelihood and don't break ties to simplicity, the full model is perfect, because it cannot be beaten in terms of likelihood. But then you have this criterion, Bayesian information, minimum description length, and there are plenty of ways of scoring the different structures to pick one as your best if you want. You could also be more Bayesian and not pick one, and then assume that all of them have a certain probability and then average over all that. But let's not go into that right now. A second way of learning, and very common in the causality area, is to try to find to do some tests among variables, so statistical tests, and find independence, conditions, independencies, then dependencies, and then build a graph compatible to that. That's another way of trying to learn the structure. With each one with different properties. I'm not going there because I'm over time already. But just to mention the parameter learning, so if you have the structure, then learning the parameters for this precise model, it's a quite standard technique here. Typically, you do maximum likelihood estimation for those small local tables, or you do a Bayesian updating. So you typically assume a multinomial Dirichlet, conjugacy, and everything goes very nicely on the computations. But basically, what you do in both these cases, because we are talking about multinomial data in this case, so you just like frequencies basically with some penalization, if you will, and you get the parameters of your model if the structure is fixed. The correct thing would be to learn both at the same time if you want to have a model, but it's also not that trivial. So you have to then, again, find trade-offs on the computation of this. Learning the model is also hard. So it's not easy to learn the model either, because you can imagine there are many possible graphs. So finding the best one is not necessarily easy. So sorry for this very quick dive into Bayesian networks. You are going to have a chance to get, a bit slower on it during the other talks, because we are going to be using them. So it's really to give you a flavor. And those are, I would say, the books I like the most. It doesn't mean that they are the only available. So take this as a personal taste on the books about Bayesian networks. There is the Pro book that Fabio mentioned from reprints, and this version is the 88. But I like very much the book by Kohler and Friedman that is way more recent, and I would say easier to read than prose, but I know this is being recorded. Sorry, Yuda. I think it's a very good book. And Adnan's Darwish book is also great, especially on Bayesian networks, why Kohler goes a bit beyond that. I will pass then the ball to Alessandro. And I come back then at 2 with Credo networks, and which are extensions of Bayesian networks, but we are going to use this also in the other lectures. So the screen is still sharp, so I suppose
Okay. Okay, guys. By the way, thank you, Cassio, because I'm using your material a lot during my presentation, the very last slot of the day. But today is the AI day, so I feel like I have to start with something general about AI, and I will say that for a lot of people nowadays, AI is mostly deep learning. Okay, that's why I feel like I have to say something about deep learning. And, these kind of titles on the unreasonable success, on the reason, generally these titles are used, not always, but are used by frustrated people by the success of some other theory, while their theory is less successful, and it's my case. No, I'm joking. Okay, it's not. I can say I'm a fan of deep learning, but I'm very excited about the success. Somehow I'm more excited about the results than by the methods, by the general idea, even if they are very smart and very exciting ideas in this application. And what I want to try to do in these 20 minutes or something is just to tell you something about, okay, the recent progress of deep learning. Now, this stuff also in the general communication, in the general press, but I will insist a bit on the critical issues related to this part, which is just a part of artificial intelligence. But of course, let's say there is a kind of happy end, and the happy end is, in spite of these issues, we have a promising direction to bypass these kind of critical issues. And let's say from my, of course, biased perspective, one very promising direction for that is causal analysis. So that's why I'm trying to advocate the need of a causal approach to modern AI. So just to see where we are, AI Day. So this AI is a large, very large field. Machine learning is a part of that. Okay, you see, not all AI is machine learning. Machine learning is dominating, but there is a lot outside machine learning. Fabio was discussing these, and will be discussing these symbolic approaches, probabilistic, logic, all this stuff which are outside, which are very exciting actually. And machine learning is containing deep learning. There is a lot of machine learning approaches, probabilistic approaches, statistical techniques, which are not, strictly speaking, deep learning. Somehow they are even more exciting, but of course, deep learning is quite important field. Okay, we might have data science, which is kind of cross field. There is something we can say that all data science is AI. What we are doing today is, of course, is inside the field of AI. I'm close to deep learning. Maybe somehow Cassio is in the machine learning area. Fabio is more AI, pure AI, or whatever. But okay, this is just to give you some direction, some reference. Okay, this is just about my research institute. I'm from IDSIA. We are in very south of Switzerland. This is a small city, Lugano. And we are kind of known especially because of deep learning. One of our two scientific directors is this guy, Jürgen Spielhuber, is kind of one of the pioneers of deep learning. There is a lot of deep learning research in our institute, some important results. For instance, this LSTM is a very popular technique in neural network and is kind of invented by our director. You know, DeepMind, okay, some of the founders of DeepMind are related, are former, let's say, or students or researchers of our institute. They did a lot of research, and then they formed this startup company, and eventually they were bought by Google, and nowadays are one of the leading agencies in research in deep learning. You might ask yourself, what about this battle? Okay, my institute was founded by the inventor of this drink. The guy made a lot of money, so eventually wanted to do some research activity, and he founded more than 30 years ago our institute. Now we are affiliated with a university, but okay, historically everything starts from this battle. And okay, we are not only a deep learning institute. Our second scientific director is Marco, and Marco is a part of this community, I would say, since the very foundation of the community. I organized the SIPTA in 2017. This was Lugano. And actually, the very first edition of this school was in Lugano. The place was not so fancy as this building. The number of attendants was not so huge, like in this case. And by the way, thank also from my side to the organizers for the nice invitation. But just to say that we are, okay, we do a lot of research in the field of imprecise probability. We have a research group acting on that. We are very much in the field of probabilistic techniques and generalized probabilistic techniques. What about deep learning? Okay, you know, sometimes it happens, and it never happened to me 10 years ago, 15 years ago, to go to general audience conference to say something about AI. Long time ago, nobody was interested. Nobody in the general audience was so interested on AI. Now something changed. There is a kind of revolution, but I will call this a technological rather than a scientific revolution. We have a lot of industrial application related and based on deep learning. Okay, these are just various pictures. What you can see, some common point in all these applications of deep learning is that they are somehow related to, I would say, more sensing than reasoning activities. That we still can somehow call them intelligent, but it's more about computer vision, it's more about speech recognition. Of course, there's also text recognition with this, which is something more. This is, if you want, is control. But let's say we are more close to our senses than our brain, let me say like that. And this point is going to appear also later. And okay, this kind of technological revolution was somehow the result of a synergy between different components. And if you want, the theory behind deep learning was not that new. Some general ideas were already there since many decades. Of course, if you ask to one of our two directors, Spielhuber, he will tell us that in the 80s, during the high school, he was already designing something like that. But okay, this is just to say that the ideas were not completely new. Of course, then there was a lot of adaptation, but this was also the boom of these techniques was also related to the availability of stronger hardware and, of course, to the availability of data. These are data-driven approaches. Okay, it's not just that. The evolution, more than a revolution, technological revolution is continuing. Now, maybe you have heard about this large language models based on transformers. And by large, this means they are really large pieces of software. So the number of parameters, these are still, the basic idea is still the same if you want, but now these tools can be used also for generation of output. In this case, is generation of text. And maybe you saw this article written by an artificial intelligence, which is hard to say that was not written by a human. These are images generated by a text, armchair in the shape of the avocado, this very recent stuff. People still from the OpenAI and there's also Microsoft are doing this kind of stuff, which are very exciting, very popular. No, let's just say that the process is continuing, is very successful somehow, but there are criticalities. And okay, the first criticality already pointed out by Fabio is that, okay, the average accuracy of these techniques is generally very high. But we might have failures, and we might have failures which are somehow very subtle. Okay, let's consider this stop sign. Okay, this was a popular paper. At some point, these guys, they pointed out the fact that, okay, the image recognition is very good, the traffic sign identification is very, very accurate, but if you change some pixel for instance, using these stickers on the traffic sign, the result is going to be completely different. If you want the other examples are more in the spirit of the image, medical image shown by Fabio, which is even more malicious. But okay, this is just to say that the small changes in the input can produce a completely different output. So we have a kind of lack of robustness in the result of these techniques, which is expected. But the second critical point is that this lack of robustness comes together with the lack of explainability. Generally, we are used to say that deep learning models are most of the times like black boxes, in the sense that given the input, we get the output, but without an explanation of the reason leading to that particular output. It's not that these models are not deterministic, but we cannot explain the reason of that particular output. And this is something even more dramatic than what we had in traditional machine learning, because in traditional machine learning, we extract the features from the input objects. Let's say that this is computer vision, but this is a general consideration. I have an image, I can extract some numerical feature from my image. Long time ago, computer vision guys were doing crazy stuff to extract the silhouette of the body by some very complicated techniques to measure the distance between these markers or whatever. Then to have the numbers and send the numbers, compute the train, have some annotation with the output, and then given this data, train some traditional machine learning techniques. And in this case, in the case of a failure, it was possible to say, okay, we got a failure, and the main reason for this failure is this feature. We got that this person is not the person that was supposed to be, because in this image, the distance between this marker and this marker is more than something or whatever. This is something which is not possible in deep learning, because in deep learning, we don't have explicitly this intermediate feature extraction process. So we have the feature are in the computer vision example, the pixel itself. So eventually I can tell you that, okay, this traffic sign is going to be classified in a wrong way because this pixel is black, and probably my system decided because of the available data that most of the images where this pixel is black are going to be a different traffic sign. But you see that this is not a high-level explanation we can provide. So this is a limitation. And this is basically what motivated people to start researching explainable AI, which is quite important, but this has a price, because there is, and it's very clear in modern machine learning, there is a kind of trade-off. Generally speaking, the more accurate is the model, the less explainable is, and vice versa. So, okay, explainable AI research is trying somehow to distinguish between the prediction and the explanation, and some surrogate models are used for the explanation. This is one issue. Another issue is, let me call this sustainability. We are going, deep learning people is going in the direction of larger and larger model with a crazy amount of parameters, a crazy amount of data for the training. So this is the size, maybe you've heard of BERT, GPT-3 was this generative model for text. And okay, this is the scale, number of parameters, but this is a logarithmic scale. So these models are growing too much. It's clear that we cannot keep this direction for a long. You know, now also in the most popular machine learning conference, there is a kind of emerging issue. So there are some experiments that can be performed only by people from Google, from DeepMind, from Meta, from the big agents, because we just don't have enough energy, money to pay the energy resources to afford that. So this is kind of trend, but this trend is going to stop soon. Are kind of unsustainable models. This was a guy who did some computation. So to train this, we need a nuclear power plant for 3 hours. But okay, it's just to say that the amount is really kind of insane. And okay, I would say that these are practical, critical points related to deep learning. But some of the most interesting is more a philosophical point. Okay, there are discussion again, these kind of papers about the reasonable effectiveness of deep learning, the reasonable effectiveness of neural networks. But okay, this started a few years ago. This was a kind of white paper about deep learning by Antonucci. Antonucci was the author of one of the books suggested by Cassio. Is a probabilistic graphical model, a guy very influential. And okay, it was this was written during the peak of the boom of neural networks and deep learning, some maybe 5 years ago, something like that. And okay, it was observing the fact that the kind of successes related to deep learning are mostly related not to intelligent and cognitive power, but more to sensing activities. We have very good computer vision application. We have very good speech recognition. And so what we might say about that is that, okay, what a neural network is doing somehow is like approximating a function. What we call vision is basically a function that transforms an image perceived by our eyes in some kind of higher level information. This function is definitely a complicated function, but not so complicated. We know that deep neural networks are, they call it universal approximators. So in principle, they can approximate somehow any function, provided that we have a sufficient amount of data to train them. And so what we have realized during the last 10 years is that what we call vision is a function, but it's not so complicated. And the amount of data we can reasonably collect, at least in some specific application, is enough to obtain a good approximation of this function. And the same is probably true for speech recognition. And now the same is probably true, we're starting to realize, for language, not only language understanding, but also language understanding, but at a deeper level. Okay, maybe this is going to be true for any kind of intelligent behavior, but at this stage is still only true for, let me say like that, low-level activities, sensing activities. And this is the natural field of application for these techniques. But somehow, as people working in artificial intelligence, we should be more ambitious. So we should go for something more than that. Okay, we are good in doing prediction. Okay, this is the point of Julia Perl, which is the inventor of Bayesian networks. But somehow, okay? But he also keeps doing research, and now is evolving his research on graphical models in the direction of causal analysis. Since many years, he's probably the most influential researcher in this field. And okay, if our final goal is not only to make a prediction based on observation and eventually based on correlation, we need something more than deep learning and pure data-driven approaches. I'm about to finish. Let me just use this very nice image from the book of Pearl. It's called the Book of Why. It's a recent book on causality. And actually, okay, it's like the 3 levels of knowledge. And the point of Pearl is that, okay, machine learning, deep learning is a kind of ladder, and machine learning is just on the first rung, on the first level of this ladder. Machine learning is about learning correlation based on observation. So we are talking about observations, and then the question we can answer at this stage is, okay, I have an observation, and this observation is going to update my beliefs, exactly as Cassio was doing with the Bayesian network. Okay, after the observation of x2 equal to something, I can change, I can update my probabilities for x5 equal to something else. This is nice. This is very useful in lots of applications, but this might not be enough. So we need to somehow move up and move to a second layer where we do not only observations, but intervention, where we might possibly change the state of some of the variables of this system in order to obtain something. An example is reinforcement learning. I was playing chess, playing games, doing control, driving. Eventually, are in this spirit. And this is not exactly the same, because if I observe this quantity to be in a state, the way I will update my knowledge is different than from the case in which I intervene on this quantity, I change the value of, I modify the value of this function, and the updated probabilities, generally speaking, is going to be different. And an important point of Pearl with this image is that moving to a second layer requires a different technologies. Deep learning is on the first layer. If we want to move to the second layer, we need something else, a different formalism. So, and this is what I try to discuss, at least one of the possible formalism in the last part of the day. And there is even a third layer, which is even more ambitious, which is about counterfactual analysis, which is still about intervention, but let's say, what if intervention? So let's say that in this world, in this situation, I observed something, and I ask myself about what will be the result of the variable of interest in a different scenario in which I manually change something. And typically this is a counterfactual analysis, because we have a kind of potential contradiction between what we observe in reality and what we imagine we can change. So you see, this is even more ambitious, and this requires an even more sophisticated machinery and formalism. And this is the point where this is my argument. This is what I'm going to defend in the fourth slot of the day, where imprecise probability can be used. There is a stronger connection between structural causal models, which are what we use at this stage, what people is using at this stage, and Cradle networks and imprecise probabilities. I'm done. So this was really just to introduce the discussion about causal analysis, which will be at 4 p.m. Of course, there is a general discussion about what is the next direction, in which direction the current deep learning approaches should evolve. Fabio mentioned neurosymbolic, which is like to merge, let's say, the brain and the eyes. The eyes are the deep learning, the brain is the symbolic reasoning. If you want, causality is in the same spirit, but is even more ambitious. okay? Because of this idea of the counterfactual. So it's a kind of proposal for a possibly, there are a lot of people working nowadays in this direction for causal AI, causal machine learning, causal reinforcement learning, and I will try to say something about that in 4 p.m. That's it. Thank you for your time, guys.